Good morning, everyone, and welcome back. So today we are going to talk about how we apply Fourier transform in analyzing electrical circuits. So I believe we ended our discussion in the last class with that. We actually saw how the impedance of capacitors and inductors directly can be derived from by the application of Fourier transform in electrical circuits. So when you represent impedances uh, through impedances with an expression that involves something like j omega, what you are doing essentially, you are representing the Fourier transform of the circuit, right? So when you studied circuit theory, you actually studied when you did something called the sinusoidal steady state analysis, where the power supply would have been an AC and you calculated the impedance of the circuit, and accordingly you calculated the voltage across the elements and current through certain elements and such and such. What you actually did under the hood, you applied Fourier transform on the circuit itself, right? That is something you studied earlier, and we saw an example, or rather a recap of that in the last class, right? So today we are going to continue from where we left off in the last class, and we shall talk about a few important things that we kind of glossed over, and we shall kind of establish a few important ideas here in this class. But in any case, I shall be waiting for 2 more minutes so that more people can join here, and then I shall continue today's discussion. Again, please let me know if the audio and video quality are fine. All right. So once again, good morning to you all and welcome back. So we are going to start our discussion right now. Okay. I would hope more people would gradually join. So let's talk about our topic at hand here. You might probably have a certain recollection that when we talked about that electrical circuits, those electrical circuits like simple capacitors, inductors, and we again solved our simple RC series circuit, we said something very important. We said that if I excite a linear time invariant system with a sinusoidal input, in the output also, in the steady state, we get a sinusoid, right? We vaguely told you this idea of linear time invariant system, and the idea is quite understandable, right? If I have an electrical equipment or an electrical circuit that runs with AC, okay, purely electrical circuits that consists of resistance, capacitors, and inductors, then if I excite the circuit with a sinusoid like a pure AC supply, then all the voltages, all the currents, everything inside the circuit, all the voltages across all the elements, all the currents through all the elements, all of those are going to be sinusoids, right? You already know these things, right, from your basic electrical engineering and circuit theory classes, right? You have this idea, right? So, right. But the thing is, why is that true? Today we are going to see why that idea is true. That when I excite a linear, again, a basic electrical circuit like that consists of resistors, capacitors, and inductors can be considered to be something called a linear time invariant system, right? Because all the elements if they are ideal in nature. So ideal, all the elements, all the elements, if they are ideal in nature, they can be considered to be linear, right? So for example, if I have an electrical circuit that consists of ideal resistors, capacitors and inductors, all the individual elements are linear in nature, okay, and time invariant in nature. And again, this terminology has been cleared up long ago, right? Again, if you want a recap class on this, I can do that without any issue. But the thing is that a simple electrical circuit can be considered to be a linear time invariant system. Okay, an electronic circuit probably cannot be considered to be a linear circuit because there will be plenty of non-linear elements. Like even if you have a simple diode, it's a non-linear element, right? So yes, it does not support linearity, and based on that, you can no longer consider the circuit to be a linear circuit. But as far as pure electrical circuits are concerned, they can be considered for the most part to be linear time invariant circuit. Okay, so linear time invariant systems, right? And if I am using if theoretically all the elements are ideal, okay, so I have ideal resistors, ideal capacitors, ideal inductors, they are all perfectly linear and time invariant elements. So the entire electrical circuit that we get is linear and time invariant. And the property that we say while teaching circuit theory or basic electrical engineering, that if I have an electrical circuit and I excite the circuit with an AC supply, okay, which is represented through a sinusoid, then all the outputs, so outputs are namely responses of elements like currents going through elements and voltages that appear across elements in the steady state, are also going to be sinusoids. So that is something you know, right? And you do these calculations through phasors, right? Okay, you apply phasor, you multiply their amplitudes and add or subtract their phase angles, right? You do this kind of computation, right? But today we are going to see where this computation actually comes from, and that computation is not just applicable for electrical circuits. That kind of computation is actually applicable for any linear time invariant system, namely an LTI system in short. For any LTI system, this kind of discussion is actually valid. So let's start with that. And again, anytime you have any query, feel free to post them on the live chat. I'm continuously monitoring the live chat here, and if you post a question, I will definitely be answering your question. And again, in my opinion, there is no stupid question, right? You can ask whatever you want here, as long as it is related to the subject. I will definitely answer it. Okay, so let's start with our topic 1 here. So our first topic of discussion is the concept of frequency response and sinusoidal steady state. Okay, so the thing I introduced so far. Okay. Let's consider a linear time invariant system. And again, since this is one of those subjects where everything I say kind of hovers around or stands on the shoulder of the things I told you earlier. So you have to recall a few things, namely the impulse response, okay, namely a few Fourier transforms, a few things, and such, right? So I would assume that you recall all those things. So now let's consider the concept of sinusoidal steady state and frequency response. Let's see what I mean. All right, so that's the box representing an LTI system, right? So this is an LTI system. LTI stands for linear and time invariant. So it's a linear time invariant system. And this system has an impulse response of ht. So when I excite this system with delta t, that is the unit impulse input, this becomes the output. Okay, this becomes the output, right? All right, there is no issue with that. Okay, now with that said, when I excite this system with any generic input, say xt, okay, I also have the output here, which is represented through by yt. Okay, and I already know by whatever discussions we had that if the impulse response of a system is ht, then that is representative of the output of the system when the input is a unit impulse, right? But what if the input is something else? For any other signal, xt, okay, that is applied to a system which has an impulse response of ht, the output can be calculated through something called the convolution of these two signals, the impulse response signal and yes, those who are saying we had some issues with the understanding of the last class's discussion, we shall have that, don't worry. We shall once again discuss whatever we did in the last class. Of course, we're going to do that with a slightly different perspective. Right. So the output here is going to be xt convolved with yt. So is there any confusion with this? Absolutely not. And from the convolution theorem of Fourier transform, if the Fourier transform of yt is y omega, and just one more thing, one of you asked me through an email that if you follow Oppenheim's book, it does not write x omega, it writes something like xj omega. Okay, and the thing is that you shouldn't be confused about this. The idea is that this is just a different notation. Okay, instead of x omega or instead of y omega, if you write xj omega or yj omega or things like that, there would be no change in any of the derivations whatsoever. Okay, any of the formula, nothing will change. This is just a different notation. Some people like to write x omega, some people like to write xj omega, right? So that's a different notation entirely. So if you want to use this notation, just write xj omega, and you don't have to literally, you don't have to change any of the derivations, any of the expressions, nothing. Okay, none of the expressions need to be changed. Okay, you just have to write down xj omega wherever you want to write x omega, and that's it. But don't think about replacing all the omegas with j omega. Okay, that is not what happens here. Okay, don't think about replacing all the omegas with j omegas, right? Because that has been taken care of by us. Okay, that has already been taken care of by the calculations we have done so far. So if you want to write j omega in the as a functional form, yeah, you can do that. But don't even think about replacing all the omegas with j omegas, because that is not what it means. It is just a different notation, right? So you might as well write yj omega here. I won't. Okay. So now with the convolution theorem, you can understand that, of course, this is the convolution in time domain. Of course, in the frequency domain, or after applying Fourier transform, if the Fourier transform of xt is x omega, Fourier transform of yt is y omega, and of course I wrote it wrong. None of you corrected me somehow. Okay. And if the Fourier transform of ht is h omega, then using the convolution theorem, we have this, right? All right. So we have that. So without any difficulty, that can be understood, right? All right. So with that said, let's now let us now bring our attention to something called sinusoidal steady state of a system. Okay, so now question is, what do I mean by sinusoidal steady state? Again, question is, what do I mean by what do I mean by steady states? Okay, what is a steady state? Question is, what is a steady state? You probably have heard this term, transient and steady state, right? So what is a steady state and what is a transient? Can anybody shed some light on this? What is transient and what is steady state? So can anybody have say something about the term steady state at least? What is a steady state? Question is, what is a steady state? Okay, someone gave me a very difficult answer. Okay, okay. So all of your answers are correct. So the idea is that if you have kept a certain system excited with the same input for a long time, the system supposedly reaches steady state under a few conditions. Okay, okay, got it? The point is, if you keep a certain system excited with a constant input for a certain amount of time or for a long amount of time, the system reaches steady state. The idea is that this is kind of vague. Okay, a system would reach a steady state only if it can reach a steady state. So there is a possibility that the system might never reach a steady state. Okay, okay, and that happens for systems that are known to be something called unstable systems. We shall discuss that later on. Okay, so if your system is so-called unstable, it would never reach a steady state. But if the system is stable, okay, rather the term is absolutely stable. If the system is absolutely stable, then if you keep the system excited with a fixed input, okay, unvarying input. Now what do I mean by unvarying? It does not talk about variance with respect to time. It kind of talks about variance with respect to frequency. We shall learn that shortly. Okay. So if I excite a system with an unvarying input, okay, and what I mean by that we shall learn shortly. Then after a long amount of time, if the system is stable or absolutely stable, then it reaches something called a steady state. Okay, got it? Now whatever happens in between when the input was first applied and when the system reached the steady state, okay, is known as the transient. Okay, so let me give you a very simple example. Say this will be a very oversimplified example. Okay, we talked about this, the charging of a capacitor, right, in the last class, a series RC circuit, and the voltage waveform kind of look like that. Okay, so if you now recall that as time goes on, if I let the time go on forever, this voltage will become equal to the voltage that appears in the input, right? This is the voltage across the capacitor. Okay, again I'm just drawing a very simple in very simple terms. Okay, so this is the voltage across the capacitor, okay, presented here, and this is the input voltage. Okay, so when I let the RC circuit when I excite the RC circuit for a very long time, what happens? After a very long time has elapsed, the voltage across the capacitor becomes equal to the input voltage. It does not necessarily have to be equal to the input voltage, but here it becomes equal to the input voltage. But the point is that there is no longer any variation in the response of the system. And again, what is the response of the system? Whatever I consider to be the output of the system. Okay, so what is the output of the system? Output of the system we consider to be the voltage across the capacitor. So after I have applied the input voltage for a very long time, what happens? The voltage across the capacitor gets fixed, right? It becomes fixed after a long time has elapsed. The voltage across the capacitor becomes fixed. So this is called a steady state. So this point that is reached here after a very long time, it's called a steady state. So after a very long time has elapsed, the system has reached something called a steady state. But before that, when there was no excitation in the circuit, okay, the voltage across the capacitor was also fixed, right? Fixed at a value of 0, right? You can understand the voltage across the capacitor was also fixed before I applied any voltage in the circuit, right? So that was also fixed. Got it? So that was fixed at a value of 0, right? So this was also a steady state. This was also a steady state. Okay, This was also a steady state. You get the point, I think, right? So steady states are those states for which you have achieved the states after applying the same input or same excitations for a very long amount of time. So before applying a certain DC voltage here in the circuit, okay, the circuit has been left open for a very long time. So you can think as if there was zero voltage that was being applied into the circuit for a very long time, right? For a very long time there was zero voltage being applied on the circuit. So the circuit had one steady state, right? So a single circuit or a single system can have multiple steady states, and probably has multiple steady states. So this is one of the steady states. So which was when the capacitor was when the circuit was in turned off condition. So turned off means you can consider that the input was zero for a very long time. So this was the steady state. Okay, and again I applied I turned on the switch, so I applied a DC voltage at t equal to 0, and when I applied a DC voltage at t equal to 0, what happens? The voltage across the capacitor steadily rose and then reached another steady state where the voltage across the capacitor is now fixed at the voltage which is equal to the input voltage. Okay, so this equal to is not a matter, but it's fixed. That's the important point here. The voltage across the capacitor is now fixed, so that's another steady state. But whatever happens in between two successive steady states, so this is one steady state, and from this steady state the circuit reached another steady state. So whatever happens in between two successive steady states is known as the transient state. Okay, so what is a transient? A transient is nothing but the response of a system that you can see between two successive steady states. That is entirely the definition of transients. So it was in one of the steady states, then it reached another steady state. So in between those, whatever states I see is known as the transient, right? So transient basically means transition from one steady state into another. Now again, if I discharge the circuit, okay, discharge the electrical circuit, of course the voltage will drop, it will reach the original steady state again. Okay, if I discharge the electrical circuit again, if I short the input and give it 0 volt for example, so the circuit will automatically discharge itself and the voltage will become 0 across the capacitor after a long amount of time. So I would say from this steady state the circuit has once again reached this steady state. Okay, and whatever happened in between is another transient. So transients are nothing but what happens between two successive steady states. And what are steady states? Steady states are those states achieved by stable circuits or stable systems. Stable systems after getting the same excitation for a very long time. Okay, so I think I kind of taught you this idea by waving my hands, okay, without using any complicated mathematics, because there is indeed complicated mathematics behind all this and those things are actually taught in digital signal processing, because there you have to study a few more important issues regarding this. But let me know if the idea is clear. Okay. So if somebody asks you what is transient, tell them about the steady states. Okay, what a steady state is, and then tell them that anything that happens in the circuit between two successive steady states is known as transient. Right? That's the mathematical definition here, really. Okay, and with that there can be many mathematical consequences here, of course. Okay. Yeah, what about 8085 microprocessor? Yeah. So once upon a time I used to teach electromagnetic field theory, and I nowadays teach my microprocessor, signals and systems, control systems, digital signal processing. I also once upon a time taught communication engineering. Yeah, subjects like that. All right. All right. All right. So is that idea clear here? All right. Please let me know if you have any query regarding the definition of transients and steady states. All right. So it's very simple to understand, right? So now, what I claimed earlier but did not bother proving was that if I excite a linear time invariant system for a very long time with a sinusoidal input, the output is also sinusoidal. So the moment I say very long time, you have to understand that I mean to say that the system is capable of reaching a steady state, right? Right? So let's copy and paste this again. I told you copy pasting is the most pleasurable thing in the world, right? Right. Okay. All right. Now I'm exciting this system with a sinusoid. Now, of course, those who do signal processing and study signals and systems, of course, things like that, people like me, okay, the most, what should I say? The good sinusoid is a cosine, not a sine, okay. So what I mean is this. Instead of writing, so if I want to show you what is the output of this system when a sinusoid is applied, I usually write a cosine. Or rather, instead of omega t, let's consider a constant frequency. Let's consider that omega naught. Okay, and why do we not consider sine? Okay, there are reasons for that, but again, you can understand that cosine and sine, they are identical in nature. Yeah? Just do a 90-degree phase shift. If you do a 90-degree phase shift, you get the same result, right? You get the same results. But if I write a cosinusoid here, my calculations would become slightly more simpler, slightly more easy to understand, right? And of course, in the Fourier transform, you don't have a j. For this, in the Fourier transform, you don't have any complex quantity. That's why that's kind of the reason we try to avoid writing sine here when I'm discussing this. But again, anything that is applicable with a cosine shall also be applicable with a sine, right? But let's for a moment see that, say this is a cosinusoid but with a certain phase angle, right? So I applied a cosinusoid with a certain phase angle, of course, right? So of course, understandably, if this phase angle is minus 90 degree, that is going to be a sinusoid. So you can now put your desired phase here. If you put a minus 90 degree phase, it becomes a sine. Okay. Okay, it no longer remains a cosine, it becomes a sine. But that is why I'm saying, okay, I'm simplifying my calculation by writing a cosine here. And you can do whatever you want, right? Nobody is going to stop you from that. All right. Now I'm trying to figure out what is the output. But not just what is the output, but the output of the system when this input has been there for a very long time. But my question is, how am I going to ensure that this input has been there for a very long time? Again, let me restate my question. I am trying to figure out what is the steady state output of this circuit or system, for example. I am trying to figure out what is the steady state output of this system. But in order for it to reach steady state, the input needs to be there for a very long time. But who is going to ensure that this input has been there for a very long time? Who is going to ensure that? Or rather, how am I going to mathematically ensure that this input has been there for a very long time? How am I going to ensure that? Or how have I ensured that? Can anybody have some idea on that? Okay. Maybe you won't be able to tell me, so let me explain this. Okay. So often you have seen that we represent our signals. Say for example, we represent our signals with a ut multiplied with it, right? For example, if I say cos t ut, okay, and we said that we are making the signal causal with this, right? This signal is becoming causal with this. So what I mean by that, of course you already know the idea behind this, that ut is a unit step, and unit step has a value of 0 as long as t is lesser than 0. As long as t is smaller than 0, ut has a value of 0. All right, so since ut has a value of 0 as long as t is less than 0, then this product is going to be 0 as long as t is less than 0. But afterwards, after t is equal to 0, after t is equal to 0, so when t is greater than 0, this has a value of 1. So whatever is the value of cos t, that appears as a value of xt. So this signal essentially looks like this. This signal looks like a 0 as long as t is less than 0, but afterwards, so let's instead of writing cos here, so let's write sine, okay, because I'm just showing you an example so that you understand what I'm saying here. Okay, so that's going to be the output. Again, very poor drawing, but this will have to do. All right, so the idea is that there was nothing that was happening up until t equal to 0, right? There was nothing that was happening up until t equal to 0, right? Do you understand what I'm saying? Though, so when I applied this input to the circuit was probably in a steady state already. Okay, what kind of steady state? When the excitation is 0, right? When I apply this, what does it mean? It means that I have a sinusoidal source. Okay, applying this kind of a voltage, for example, say if this is my voltage, if this is the voltage, applying this kind of a voltage simply means that I have this voltage sin t. Okay, but then there was a switch. That I connected at t equal to 0, and there was whatever electrical circuit I had, something like that. So this is how I have ut multiplied with it. So having a ut multiplied simply means the switch was turned on at t equal to 0. That is what it means. So the voltage that was appearing across the circuit was 0 before t equal to 0, but the switch was turned on at t equal to 0, something like that, right? So when the switch was turned off, the circuit had one of its steady states, just like this one. When it was in off state, that is also considered to be one of the steady states, right? So if the circuit was left open for a very long time, everything got discharged, everything got demagnetized, none of them had any energy in them, and as such the circuit had reached one of its steady states. But then if we apply a voltage across it at t equal to 0, what happens? So basically we are turning a switch on. What happens? We are making it reach another steady state. So now I shall have to wait for a very long time for it to reach another steady state, right? Theoretically, you have to wait for infinite amount of time. Theoretically, this reaches steady state when t goes to infinity, right? Theoretically, it reaches a steady state when t goes to infinity, or rather that's ideally the situation. Okay, so it's a limiting case, but unfortunately, or rather fortunately for us, when t is sufficiently large, okay, and what do I mean by sufficiently? That's a qualitative measure. We shall soon look at that. When time has reached, so when enough time has elapsed, so read this as this: when enough time has elapsed, when enough time has elapsed. So this state is reached when enough time has elapsed. So that is the point here. Okay, so enough could be very different things for different situations. So we shall talk about that. But here, try to understand, the circuit probably had a steady state before t equal to 0. and then I shall have to wait for a very long time for the circuit to reach another steady state, right, after I applied this. All right, so that is what happens when I have something like a ut multiplied with it. When I have something like a ut multiplied with it, right, because ut ensures that the signal actually starts at t equal to 0, and before that the signal stays off, so which means that the value of the signal was 0 before t equal to 0. That is what it ensures. But what about this? What about, so this is sin t ut, but what about just sin t? If I just say sin t, so if I just say sin t, now what am I saying here? What am I trying to say here? So again, this is my new xt here. This is just sin t. Okay, my point is that try to understand, you are standing at t equal to 0, but from your perspective, okay, but from your perspective, when did this signal start? When did this signal start? From your perspective, when did this signal start? But if you are standing at 0 for here, for this one, with a signal multiplied with ut, if you are standing here at t equal to 0, yes, answer is the signal started at t equal to 0. Now here, for a signal which is just sin t without a ut multiplied with it, if I ask you, you are standing at t equal to 0. From your perspective, when did the signal start? Did you get my question? When did the signal start? That's my question here. So can somebody answer? When did the signal start? Yes, absolutely. The signal actually, so one of you got the answer absolutely correct. The signal actually started at t equal to minus infinity, t tending to minus infinity. So technically, you can go as far back as you want here. You would still see this signal being there. But for this one, the signal, the term is the signal suddenly appeared at t equal to 0. So try to understand. This signal suddenly appeared at t equal to 0. So the term is suddenly. Suddenly appeared at t equal to 0. So this signal suddenly appeared at t equal to 0, right? The term is suddenly. So when a signal suddenly changes at a point of time, so what happens? That moves the system into a transient state until the next steady state is reached by the system. But here the signal has been there for, again, this is quote unquote, okay, a very long time. So here this signal has been there for a very long time, because you can go as far as you want. Okay, this signal still should have existed, right? Because you don't have ut multiplied here. But for this one, you can consider the signal to be suddenly appearing at a certain point of time. Okay, so it moved the system, probably should have moved the system from one steady state into another. Now this signal, which does not have ut multiplied with it, indicates that this signal has been there for a very long time. So this is the signal that probably has been exciting the circuit for a very long time. And what is very long time? This is a relative term, and we shall explain what I mean by very long term, right? Very long time. For example, if you are so what is infinity? Okay, for example, if you are a daily wage earner who earns like something like 200 rupees or 100 rupees per day, so if you give that person say 50,000 rupees, so it's like infinity for that person, right? And someone who earns like 50,000 rupees per month or per day, for example, okay, you give them 50,000 rupees. That's a pretty simple amount of money. That's not infinity. But for someone who earns 100 rupees per day, for that person 50,000 would be like infinity, right? So yes, that term infinity here is also like relative, and we shall discuss that quickly. later on, I mean in today's class, of course, right? But try to understand that this signal from the perspective of the circuit has been there for a very long time, and this signal from the perspective of the circuit has suddenly appeared. So if that idea is clear, then we can proceed with our next point of discussion here. Right. So yes, what is big or what is small, this entire idea is kind of relative, right? All right, all right, all right. So you got the point. So now question, let me go back to my question. How did I ensure that this system had a steady state? I ensured just by not having a UT here. If I had a UT here, it would mean that this signal suddenly appeared at t equal to 0. But since I don't have a UT multiplied with this, okay, it means that this signal has been there for a very long time, and as such, this circuit had enough time to reach its steady state. Okay, so since I don't have UT multiplied here, it indicates that this signal has been there for a very long time, and as such, this circuit or this system had enough time to reach its steady state. Get the point? Right? Again, if you have any confusion so far, feel free to ask. All right. So with that said, the circuit has an impulse response of ht and input, and now this could be anything. And input was xt, that was a cosinusoid omega naught t plus phi. So this has a frequency of omega naught radian per second, and phi is just a phase angle, right? All right, that was the input, right? And again, if you have any query during the class, okay, during any discussion I make here, okay, so again, my job here is to make things as clear as possible. So you should have the theoretical constructs very clear with you, okay? Because there are many assumptions we make in this entire subject that go unexplained in many of the classes, right? So we are trying to explain everything. That is the whole point here, okay? Why things are the way they are, right? So let's consider what is the Fourier transform of ht. We consider that to be h omega. And again, if you desire to write hj omega, you can, but I don't. Okay. Now, what is the Fourier transform of a cos omega naught t? What is the Fourier transform of a cos omega naught t? So that's a pi delta omega minus omega naught plus delta omega plus omega naught. Okay, omega naught is a constant. Again, this is a constant. Constant frequency. Again, unit is radian per second. All right, so that's not an issue. Now, can somebody tell me with their understanding of Fourier transform, what is going to be the Fourier transform of this? What is going to be the Fourier transform of this? Can somebody tell me? So I am calculating the Fourier transform of this. So this can be also written as a cos, you can take omega naught common. I have t plus phi by omega naught. And now can somebody tell me what is the Fourier transform of this? Therefore, the Fourier transform of a cos omega naught t plus phi by omega naught. What is the Fourier transform of this? Can somebody tell me that? So this is a time shift. Okay, this is a time shift, simple time shift for the Fourier transform. Okay, so can somebody tell me what is the Fourier transform? What is going to happen here? So this is it, and with this, basically we have to apply a time shift here. Time shift on this. Right? That's a time shift. Time shift by how much? Plus phi by omega. Right? So you probably recall that if the Fourier transform of xt is x omega, then question is, what is the Fourier transform of xt minus a? What is the Fourier transform of that? What is the Fourier transform of xt minus a? Someone is saying e to the power. So what about this one? Was it? So questions, can somebody tell me if this minus sign is okay, correct or not? Otherwise I shall have to look at the formula, because again the problem is what the problem with me is, right? I cannot recall any of the formula, so it's unfortunately let's see that. Yeah, j omega a. All right. So we have this, right? That is the time shifting property, right? Question is, how much time did I shift here? So if I have a plus sign, of course, here I get a plus sign here. So with that said, of course. So with that said, here this is the amount of shift. So this is like a here, right? This is like a here. So the answer would be simply e to the power j omega, and instead of a I have phi by omega naught. So everything is on top of this exponential, and then x omega, and x omega is, of course, x omega is a pi delta omega minus omega 0 plus delta omega minus omega plus omega 0. Yeah. All right. So please let me know if this is correct, right? So I know for the signal I have xt, which is this one, for this particular signal xt, right? So this has a Fourier transform of a pi e to the power j omega phi omega naught, and now delta omega minus omega naught, okay, plus delta omega plus omega naught. All right. Now please somebody tell me that if you see what is going to happen right after this, of course. So if you recall now try to recall that if I have something multiplied with this delta t minus a, what happens? This is what happens. So we established this in our last class, right? Something like that happens, right? We established this in the last class, right? So now you can see this e to the power j omega phi omega naught, this thing is multiplied with these deltas, right? Right? Please let me know if you don't understand what I'm saying here. So with this step, after this I can write a pi, and I have e to the power j omega phi by omega naught into delta. So this entire thing is on top of e, omega minus omega naught, and then plus e to the power j omega phi by omega naught into delta. This is not a convolution, huh? This is just a multiplication, right? We had this. Now of course this is like a function of omega, so like just like this one, of course understandably, if this is like omega, this is in omega for example, same thing, right? It's a change in the name of the variable, right? Does not matter. So this is the function of omega, right? So let's write a function of omega. So this is like this one, it's a function of omega, right? It's a function of omega, right? Omega naught is a constant, try to understand. Phi is a constant, omega naught is also a constant. Then again, let me just explain this. And constant phase. Phase in radian. What is the unit of phase? That's radian, right? Not degrees. So phi and omega naught are constants, so it's a function of omega, of course, understandably. And this is like f omega multiplied with delta omega minus omega naught. So a is this omega naught, that's the constant. So with that said, what is the result of this multiplication? What is the result of this multiplication? So I think you get that. Therefore xt has a Fourier transform. So I'm just doing this multiplication here. So the result is a pi, and of course now here, of course by this definition, omega in this function needs to be replaced by omega naught, right? Omega in this function needs to be replaced by omega naught. So e to the power j omega naught phi by omega naught. Of course omega naught means omega 0, huh? Okay, and I have delta omega minus omega naught. All right, and plus with the same thing, if I have a plus sign here, I would have a minus sign here and a plus sign here, right? So you know that already. So you can consider a plus a to be minus of minus a, right? So with that said, of course this omega here in this function will have to be replaced by minus omega naught. So I have e to the power minus j omega naught phi. I know my head is blocking everything. Omega naught and delta omega plus omega naught. Please somebody tell me if this calculation is understood. We had a omega here, we also had a omega here, but because of this multiplication with the Dirac delta or unit impulse, I applied this property of unit impulse, right? Right? So here in this case, a was just minus omega naught. I just put minus omega naught. So in this place. So if this is understood or not, please let me know. Because in the next line, I can do a very simple simplification. I can cancel out these omega naughts. So I would have a pi, and then I would have e to the power j phi and delta. Now this is a constant, omega minus omega naught plus e to the power minus j phi delta omega plus omega naught. All right, so that's understood, right? Again, feel free to ask any question that you might have with this. Feel free to ask any question that you might have with this. All right, so that's the Fourier transform, right? So rather, instead of writing x with this symbol, let me write x omega, right? So this is just x omega, right? That's the Fourier transform of the input we have been dealing with so far. So that's my x omega, right? Right? No issues with that, right? So of course we know h omega is the Fourier transform of the impulse response, and that could be anything. That could be any signal. Okay, the system can be anything as long as the system is linear time invariant. This is whatever we're going to discuss here is going to be applicable. Okay, so with that said, what is the output? What is the Fourier transform of the output? The Fourier transform of the output is the product of the Fourier transform of the input with the Fourier transform of the impulse response. Right? This is the Fourier transform of the impulse response. Of course, this is the Fourier transform of HT, the impulse response, right? So with that said, let's do that. So I already know about this, right? I already know about this. This is x omega. So let's write that. And h omega is this one. So I have a pi, that's a constant, into h omega into this entire thing. Why am I writing this? Let's copy paste. All right. So this is a pi and this thing is x omega, and then I have h omega multiplied. Right. All right. Now we have the same situation once again. What same situation I'm talking about? The same situation I'm talking about is this one. It will be evident momentarily. Here, if I go inside this and multiply this with all these two terms, e to the power j phi is a constant because phi itself is a constant. So I have e to the power j phi, then I have multiplied with h omega, then I have multiplied with delta omega minus omega naught. Again, look very carefully. This is delta multiplied with h omega, which is a function of omega. So of course that property that I told you moments ago and we proved in the last class will again be applicable here, right? And similarly I have a plus e to the power minus j phi into h omega into delta omega plus omega 0, and as such. Please let me know if this is understood. If this is understood or not. Understood? I think this is understood, right? All right. Feel free to ask if you have any query regarding this. All right. So with that said, I'm writing a pi because this is not, again, I mean, whatever I'm trying to prove here, none of the teachers actually, most of the teachers teaching this subject do not even try to reach these points because these are kind of very difficult things to actually prove and explain properly rather than just telling them that this happens, telling the students that this happens. So h omega, so h instead of h omega, I would write h omega naught because of this. So this is being replaced by that constant quantity here because of this multiplication with delta. And I have e to the power minus j phi e to the minus j phi, and here I would have minus omega here. So I would have h of minus omega and delta omega plus omega naught. All right. So we have this expression here. We have this expression here. So again, feel free to ask any question that you probably have here. Okay. All right. Now try to understand that this is no longer a function of omega. This is also no longer a function of omega, right? This entire thing is a function, is a constant. This is entirely irrespective of omega. This is a constant. Omega naught is a constant. So this entire term e to the power j phi h omega naught is a constant. Similarly, e to the power minus j phi h minus omega, that's also a constant. So these two terms are constants. So this is as good as this a pi, right? This is just a fixed constant value, constant number, right? I think that idea is clear, right? So this is just a constant number, right? Okay, someone is saying, why do I put minus omega? Because of this. If this is minus, then this is fine, right? This is the property. What if in this same property a is a positive quantity? What if a is a positive quantity? Let me just what if in the same property A is a positive quantity, then what would I have? I would have F omega delta omega plus A, right? So with that, so we have situations like that, delta omega plus A, right? Plus A. So what is plus A? Plus A is just minus minus A, right? Minus minus A. So with that said, I would have F. So with this property, just put with this property, just think about this, but consider this to be minus of minus A. So I have minus A here and delta whatever remains, because this plus A can be considered to be minus of minus A, right? I think that's understood, right? Alright, because you that property, so I put omega naught when this is a minus sign here, there is a minus sign here, and when there is a plus sign I can consider that to be minus of minus omega naught, so I just put minus omega naught. I think that's clear, right? Again, if you still have any query, feel free to ask. So that's the Fourier transform of the output. That's the Fourier transform of the output, right? I think it's clear, right? So this is the Fourier transform of the output. Then what is the output? The output, of course, is going to be the inverse Fourier transform of y omega. So y omega is the Fourier transform of the output. Then what is the output? Output is the inverse Fourier transform of y omega. So the inverse Fourier transform on this whole thing, right? On this whole thing. So let's apply that. So inverse Fourier transform on this entire story here, whatever I have here. So if I take this, bring it here, pull it down here, and it's going beyond the hold on. Oh, is that the discussion? Yes, absolutely. Thank you very much for, again, when you, what should I say, when you figure out this kind of small mistakes, of course, in my mind, I of course had minus omega naught, right? So it essentially means that you people are following quite nicely, or rather, you're putting the required amount of attention in this subject. Thank you very much for correcting this. All right, so I have the Fourier transform on this, absolutely. Of course, right? All right, so now of course Fourier transform is a linear operation, so it applies independently on this, and then again these things are constants. So I have okay. Some things got lost in translation then. Right? So this Fourier transform is going to be applied independently on this and independently on this, right? So again, when the Fourier transform gets applied independently on this, a pi e to the power j phi h omega naught, all these are constants. So all this can happily go outside this, right? All right. Plus similarly, when the Fourier transform gets independently applied on a pi e to the power minus j phi h minus omega naught delta omega plus omega naught, this entire thing a phi e to the power minus j phi h minus omega naught, this entire thing is a constant, so that can go outside. So a pi e to the power minus j phi h of minus omega naught, and then I have the Fourier transform of delta omega plus omega naught here. Sorry, inverse Fourier transform, very sorry. Yeah, inverse Fourier transform, right? All right. Now please do tell me whose inverse Fourier transform is, what is the inverse Fourier transform of this? What is the inverse Fourier transform of this? Can somebody tell me? Or rather I can calculate it very quickly. Okay, so if somebody can tell me, I'll be very happy. If somebody can't, let's calculate then, right? So this is the best weapon I have. Calculate everything. So let's calculate the inverse Fourier transform of delta omega minus a. And I can now directly apply the integration, because doing an integration with delta is a pleasure, right? So I have 1 by 2 pi integration from minus infinity to infinity delta omega minus a e to the power j omega t d omega, right? Yeah, so that's going to be 1 by 2 pi. Some of you can still remember some formula, but unfortunately I cannot. I'm really bad at remembering any expression, right? But I know the property of Dirac delta, right? So omega has to be replaced by a. So the answer is going to be, so here, so if this is your f omega, so answer would be e to the power j a t. That's going to be the answer. So the answer is going to be 1 by 2 pi e to the power j a t, right? So I now have this, the inverse Fourier transform of delta t minus omega naught. That's going to be 1 by 2 pi e to the power j omega naught t, right? All right. And similarly, the inverse Fourier transform of delta t plus omega naught, that's going to be 1 by 2 pi e to the power minus j omega naught t. Same thing, just consider this to be minus of minus omega naught, right? Is there any confusion with this? Absolutely not, I think, right? So let's go back here. So I have and let's have, okay, let's keep it, a pi e to the power j phi h omega naught, all these are constants, and here I have 1 by 2 pi e to the power j omega naught t, right, plus a pi e to the power minus j phi h minus omega naught, and that's going to be 1 by 2 pi e to the power minus j omega naught t. So those are the inverse Fourier transform of these quantities, right? And again, let me get rid of these like these never existed, like I remember everything, right? So I recall all the formula and none of the calculations I did ever existed, right? So now we can cancel out this pi. So I have a by 2. E to the power j phi, and I have h omega naught, and then I have e to the power j omega naught t, right? And then of course similarly I have a by 2, same thing, pi cancels out, and I have a by 2 e to the power minus j phi h of minus omega naught into e to the power minus j omega naught t. Now of course I have done the inverse Fourier transform, so omega does not appear anywhere, right? So only I have omega naught, which is a constant. It's a constant frequency, right? Hold on. We're doing this elaborate derivation to prove a very important point about linear time invariant systems, and we shall go back to that. All right. So I now have a by 2 common out of these. Okay. And if I take a by 2 common out of these, so now I want to write a few things here. Try to understand what I want to write here. Okay, I want to bring these terms together, these two terms together, e to the power j phi into e to the power j omega naught j phi and e to the power j omega naught t. These two terms together, I want to bring them together. So I have e to the power j omega naught t plus phi, and then I have h omega naught. So again, if you have any confusion, okay, and try to follow properly. If you think that I have written something wrong, I probably have written something wrong. Okay, so try pointing me out. And here I am taking minus j, this term minus j minus j, and so I would have omega naught t plus phi, and then I would have h of minus omega naught. All right, all right. So there is no confusion with this, right? Now what is h? What is h omega? That's a complex quantity, right? What is h omega? That's a complex quantity. No confusion with this, right? It's a complex quantity. So since it's a complex quantity, now let's look at this. Now let's think about this. What is h omega? H omega, I did not write h omega naught. This is h omega. What is h omega? H omega is this, the Fourier transform of ht. So I would have ht e to the power minus j omega t dt. Then what is h omega naught? H omega naught is this. Just instead of omega, I am writing omega naught. Right? I can do that. Right? I can always do that. So I'm calculating the amplitude of a certain frequency, right? Certain particular frequency component, right? I can do that. All right. So there is no confusion with this whatsoever, right? All right. So this is a complex quantity, right? This is understandably a complex quantity, right? Now, what if I write h of minus omega naught? So understandably, I am replacing this with minus, right? With a minus sign here. So okay, so ht, I would have e to the power minus j and a minus omega naught t dt. So I just have a j omega naught t, right? Oh, okay, so one of you is saying something about the odd or evenness of h omega naught. That will not be considered at all. This is whatever I'm going to show you here. This is true. This is going to be true irrespective of whether h omega naught is a h omega is odd or even. Irrespective of that, it is going to be true. It is going to be true irrespective of that, right? So I have something like this. I have something like this. Now try to understand that. Let's just jump into complex numbers for a while and we'll see what I mean. Okay, let's talk about complex numbers. Okay, so what is a complex number? For all intents and purposes, okay, let's talk about complex numbers. What is a complex number? For all intents and purposes, a complex number is just a coordinate point. Okay, point on a 2D coordinate plane. Okay, so for example, I can have, so this coordinate is x comma y. This is also equivalently written as x plus jy. So if it's a complex number, it can be written as x plus jy. What is x plus jy? Just a point whose abscissa is x and ordinate is y. So x coordinate is x and y coordinate is y. So namely, if I say 1 comma 2, this is just 1 plus 2j, which is the point 1 comma 2. Abscissa is 2, ordinate abscissa is 1, ordinate is 2. So this length, okay, this length is y and this length is x, right? So this is just a point here, understandably, right? So again, why am I saying all these things? Because I need to make things very clear here that nothing should look ad hoc in our discussion. Okay, now what about this length? What about this length? This length is, of course, by means of Pythagoras theorem, is root over x square plus y square, and length is positive, right? So this is the Pythagorean distance between the origin here and this point here, right? This is known as far as the complex representation goes. If this is represented with z, okay, this distance is known as the modulus of the complex number. So this is going to be root over x square plus y square, okay? And this also, if I draw this radial line, this also has an angle, and if I consider that to be theta, and if this point is on the first coordinate, then theta, of course, then from this, what is this length? If this length is mod z, what is this length? So what is sine theta? Sine theta is going to be perpendicular by hypotenuse. So y by this length, what is this length? That is mod z. So with that said, I know that y is equal to mod z sine theta. Okay, understandable, right? We know that. And what about cos theta? If I say cos theta, that's base by hypotenuse, then same again x by mod z. So I have from this x equal to mod z cos theta. All right. So what is the complex number? The complex number itself is x. What is z? Z itself is x plus jy. Z itself is x plus jy, right? So if this is x plus jy, instead of x I can write mod z cos theta. What is theta? This angle, right? And plus j, instead of y, what can I write? I can write mod z sin theta. Now mod z is a constant quantity, so it can go outside. It can be mod z, and what do I have? I have cos theta plus j sin theta. But from Euler's theorem, you know cos theta plus j sin theta is e to the power j theta. So this is another representation of a complex number. So a complex number can be represented as in Cartesian coordinates like this, and this is also known as the polar representation. In our terminology, we often write this as mod z angle theta. Mod z angle theta. So that's the complex representation here. Very simple, right? So now let's again think about what I am going to say here. So let's take a complex number again. So this is a complex number, which is, so for example, which is again a coordinate point being represented as a coordinate point. This is going to be, say for example, x plus jy, just a point x comma y, like that. Okay, so I'm considering this to be z. Okay, I'm considering this to be z. Then question is, what is z bar? You people know what is z bar? Z bar, or namely the conjugate of the complex number, and we don't put bar here. In our signal processing classes, we use a star on top, okay, as a superscript. We use a star as a superscript to denote a complex conjugate. Okay, a complex conjugate is just this x minus jy. But what is this? This is this point whose ordinate abscissa is, so basically this is x comma minus y. If this point is x comma y, this point is x comma minus y, right? Same abscissa, negative ordinate. Okay, so think about this distance, this this radial line here. Okay, what is the magnitude here? What is the distance here? Root over x square plus y square. But here for this number, same thing, same distance. Okay, but what about the angle? If this angle is theta, then this angle is minus theta, right? So what I just wanted to say, z as a complex number has a representation like this, mod z e to the power j theta. Okay, but theta is the angle, okay, calculated by tan inverse or here. So of course you can understand that, right? Tan theta will be y by x, and take the principal argument there. Then what is the complex conjugate of this? X star. Okay, x superscript star. What is the complex conjugate of this? So complex conjugate of this complex number z is the same complex number, is the complex number that has the same amplitude, right? Same modulus, but with a negative angle. So this is going to be mod z angle. So if this is this, the same distance is here, angle e to the power. So angle negative angle, right? If this is the positive angle, then this is just giving you a negative angle, right? So please let me know if this, with this discussion, if everything is fine. All right. Okay. So basically, if you have a complex number, you take the complex conjugate. What happens? Amplitude remains same. The phase angle gets a negative sign. Okay. So with that said, this thing, okay, this complex number h omega naught, for example. Okay. So moments ago I wrote that h omega naught thus try to understand. H omega naught, it is a complex number, right? It's a complex number, right? So it has an amplitude H omega naught, and it has an angle. Let's call that theta for example, for the moment. Okay, let's say angle H omega naught to be equal to theta. Let's say that. So this is e to the power j theta. That's bound to happen, right? Then what is the complex conjugate of that? That's going to be the same amplitude but with a negative angle. Okay, but with same negative angle, right? That's understood. There is no issue with that, right? There is no issue with that. Okay, all right. So I think this is understood, right? This is understood. So with that said, my question is, what was H omega naught? H omega naught was integration from this and this ht e to the power minus j omega naught t dt. Then my question is, what is the complex conjugate of this? What is the complex conjugate of this? So how did I get the complex conjugate? I get the complex conjugate by just changing the imaginary quantity, putting a minus sign over the imaginary quantity, right? So if this was jy, it has now become minus jy. So whatever is coming with j, okay, gets a minus sign. That's it. So with that said, what is the complex conjugate? Same thing. Whatever is coming with j gets a minus sign, right? So ht, so if this gets a minus sign, so right, that's the complex conjugate here. There is no difficulty understanding this, right? And again, I am considering ht to be a real signal for the most part, but same thing, it won't matter if this is a complex signal, same result will follow. Now here we calculated h of minus omega naught, and here we have calculated h star omega naught, which is the complex conjugate, and it appears they are identical. So that is, we can now say, and again you can just remove omega naught, so whatever. So we can say h of minus omega is nothing but h of complex conjugate of omega, right? So if you take a Fourier transform and calculate its complex conjugate, so it gives you the same thing with a minus sign here. And you can replace omega with omega naught and whatever and whatnot, right? So much discussion. So with that said, let's go back. We had this, right? So yt was this. Let me again copy and paste. So now go back. Now let's go back, right? So this was our yt. We have taken inverse Fourier transform happily already, right? So again, omega naught is a constant. So here in this line, I'm just writing a, so let's write everything. Let's copy paste everything once more. Why not? Hold on. Now of course, with this, here instead of writing h of minus omega naught, I can write h star omega naught. And again, this star is on the superscript, so don't confuse it with convolution. Is there any problem with this? If there is any problem with this, please let me know. I just derived this, right? All right. Not this. Okay. So with that said, now try to understand. What am I doing? Now h omega again is a complex number, right? So let's again go back. So h omega naught is mod h omega naught e to the power j theta, where this is theta. Then h star omega naught is mod h omega naught e to the power minus j theta. That is what I'm writing here. So this is going to be mod h omega naught e to the power, and with this it is going to be e to the power j theta, right? So that's how h omega naught is represented, and this is e to the power j omega naught t plus phi, and here I have mod h omega naught e to the power minus j theta, of course since this is a complex conjugate, and I have e to the power minus j omega naught t plus phi. Now here, of course, here theta is nothing but the angle of h omega naught, right? No confusion with this. All right, so h omega naught can go outside, so I have a by 2 mod h omega naught, because that's a constant from both the terms, and here I have e to the power j omega naught t plus phi plus theta. So I'm writing all of them together like that, j omega naught t plus phi plus theta, right? And here I'm writing plus, same thing here, okay, same thing, look very carefully, of course I missed a bracket, same thing, multiply them, I have e to the power minus j omega naught t plus phi plus theta. All right, so this entire thing now looks something like, and let's bring this half out inside. So I have a, now bring this here, right? So this is just like e to the power j theta plus e to the power minus j theta by 2. And what is that? So this is just like e to the power j theta plus e to the power minus j theta by 2. What is that? That's cos theta, and here this is the entire thing, right? Omega naught t plus phi plus theta, right? So again, what is theta? Omega naught t plus phi. What is theta? Theta is angle h omega naught, right? Now let's go back what we derived. What did we derive here? So in order to see what we have derived, so this is the output of the system. So what have we derived really? Let's go back. It was a very, very long derivation, but nonetheless a very useful one rather. So what have we derived? So we have derived that if I excite the linear time invariant system, okay, with a sinusoid that has been there for a very long time, so under the steady state, okay, this is going to be the output. If this is the input to the system, then this is going to be the output of the system. So this, if this is the input to the system, then this is going to be the output to the system. Let's again pull this back a little bit. All right. So my question is, now try to understand. My question is, what is the nature of the output in the steady state? What is the nature of the output in the steady state? The input was a sinusoidal, Okay, the input was the sinusoid, the output is also a sinusoid in the steady state. So I can now state, now question is try to understand what is the what has changed. I excited the system with a sinusoid for a very long time. I kept the system excited with a sinusoid for a very long time. And of course, by very long time, I mean, I let the system reach a steady state. And when the system reached a steady state, the output was also a sinusoid. But what was the difference? The difference is in the amplitude of the sinusoid and the phase angle of the sinusoid. Okay? There is a phase difference and there is a scale up or scale down in the amplitude. Right? Got the idea? Understood, right? Right? So if the input is a sinusoid, the output is also a sinusoid. No difference. Okay, only changes happened in the amplitude and the phase angle. So the phase angle changed and the amplitude changed, right? So if I represent this as B cos omega naught t plus phi 1 being the phase angle of the output, then I can say what is the ratio of the amplitude. So this is the ratio. So ratio of the okay, amplitude of the output, ratio of the amplitude of the output to that of the yes, you don't have to do the same derivation for sine. If you want a sine wave, just replace this with minus pi by 2. You got a sine. If you want a sine wave, just replace this with a minus pi by 2. You get a sine. Same derivation will follow. That's going to be equal to sine, right? I think I answered your question. Okay. Sine is just a cosine with a different phase angle. No, we shall automatically get a j because again, you can just derive the sine expression for sine by just putting phi equal to minus pi by 2. But if you want a j, look very carefully, we would have a j because the Fourier transform of in this Fourier transform, if I had a sine here, that would be pi by j already. That would be pi by j and a minus sign here. I would have a minus sign here and it would be pi by j. Same thing. There would be pi by j here and a minus sign here. No difference. No, nothing else. So automatically same thing will follow. So eventually after everything, I would have a minus sign here, I would have a minus sign here, and that 1 by j would appear here. And you can just do the same derivation just by putting phi equal to minus pi by 2, right? The same thing. So the same thing will happen. So it does not matter whether it's cos or sine or anything, right? So amplitude of the, so I think I got that answer, got it clear, right? So you could start the derivation with that. So you would have a pi by j and a minus sign in between, and that j will remain and appear here, and the minus sign would appear here. Same thing, same thing. And of course, as electrical engineers, you can always change the phase angle. Cos is nothing but a sine wave, or sine wave is nothing but a cosinusoidal wave with a different phase. So put phi equal to minus pi by 2. End of story, right? Put phi equal to minus. So this is true. This is an identity, right? This is true, and this is true for every value of phi t whatever, right? So you can just put phi equal to minus pi by 2, and you have a sine wave then. So now my point is, amplitude of the ratio of the amplitude of the output to that of the input is this b by a. That is what I'm saying here. That's nothing but, try to understand that this is a mod h omega naught by a, which is just this, right? So the ratio of the amplitude of the output sinusoid and input sinusoid is entirely determined by the Fourier transform of the impulse response. Okay, this is the Fourier transform of the impulse response, of course with a constant value of omega, right? And the phase of the output minus phase of the input what is that? It is phi 1 minus phi, right? So this was the phase of the input and this is the phase of the output. I'm saying this as phi 1. Okay, this entire thing I'm writing as phi 1. Okay, this is going to be my phi 1. Okay, so with that said, and this entire thing is going to be P. Okay, all right. So with that said, this is going to be phi plus angle of h omega naught minus phi. That's going to be angle h omega naught. So angle of the angle of the Fourier transform of the impulse response is solely responsible for changing the phase of the input. Changing the phase of the input, right? It's entirely responsible for changing the phase of the input. Or rather, it's the only thing responsible for changing the phase of the input, right? And now the only thing that can affect these is the frequency, right? So try to understand. Look very carefully at this. This ratio of the amplitudes of the output sinusoid and the input sinusoid is entirely determined by omega naught, because this entire thing is a function of omega naught. So for varying frequencies, the output will be different. For varying frequencies, the output will be different, right? So this entire thing is entirely dependent on frequency, and how much phase will be contributed by the system is also entirely determined by the frequency, right? That is why h omega naught, rather h omega, of course you can put this, okay, omega naught is just a value of this, right? H omega is known as the, not just as the impulse Fourier transform of the impulse response, but it is also known as the frequency response. How the circuit or the system behaves with varying frequencies. So if I change the frequency, how the circuit behaves. That is why it's called the frequency response. Okay, I can just put omega naught, it's a special value, right? So the idea is that h omega naught is, this is how we write it, h omega when omega is omega naught for a particular frequency, right? That's the idea. In any case, so this is known as the frequency response of the circuit. So I think I got that out of the way. So the idea is that in very clear term, that is, when a linear time invariant system is excited with a sinusoidal input, the output in the steady state is also a sinusoid whose amplitude and phase are determined by h omega. Determined by, I'm writing h omega here, right? So that's the entire statement I wanted to make. Okay, rather this is the statement I made, but without actually proving it or going into this. Now this is going to be quite evident shortly, I mean with an example of course, and we shall continue doing examples on the next class, but I wanted to make things very clear here, right? Because whatever I say should be proved, if it can be proved with the mathematical expertise we people have, right? Here I have not done any complicated mathematics whatsoever that we haven't studied earlier, right? Now, feel free to ask any question that you might have, because we are going to shortly show you how these things actually come into action. And this won't be some ad hoc representation of something. This will be something that you have studied in your circuit theory classes and basic electrical engineering classes. All right, so let's see an example. Okay, so let's talk about a simple series RC circuit again, a very simple thing. Okay, so again, this is how we actually had drawn this. Kind of something that looks like an looks like a two-port network. Now here I excited the system with any, so this is now any signal. Now in this particular scenario, this is going to be a sinusoid. Okay, this is going to be a sinusoid, and this is, I'm writing this, and of course I'm measuring the voltage across this. So this is going to be voltage across the capacitor, right? So this is the capacitance, this is the resistance. I'm considering this to be plus. All right. So in any case, the signal sign doesn't matter here. Okay. All right. So we had that. I had this this in our repertoire, and we actually did this entirely, right? So let's bring this here. All right. So now in the last class we said this could be any input, right? This could be any input, and this is considered to be the output. This was considered to be the output. So I wrote yt here and I wrote xt here, right? And I showed you that the impedance, everything, they are actually the Fourier transform of the expressions, right? They come from the Fourier transform of the expressions, right? So let's write down the expression for the moment, right? So this is the voltage across the entire circuit. Of course, if the current is IT, then of course, understandably, the voltage drop across the resistor is this, and the voltage drop across this is YT, and this is equal to the input from Kirchhoff's voltage law. And from that, we know the voltage current relationship of a capacitor. So that was given as I equal to C dV dt. So voltage across the capacitor is differentiated, multiplied with C, and we know that, right? We actually did this and cleared things up properly in the last class. So of course, I is just C dyt dt plus yt equal to xt, right? And now we applied the Fourier transform here. So if the Fourier transform of yt is y omega, then the Fourier transform of dyt dt was j omega y omega. So I had j omega rc y omega, okay, plus y omega equal to x omega. All right, and so y omega by x omega would have was 1 plus j omega rc, right? Something like that. All right, so this is the voltage across the output, and this is the input voltage, right? So that is the function we had, and we express this as h omega, right? We said this is h omega. This is the Fourier transform of the impulse response of the circuit. Now this is right, I think this is quite evident, right? This was the impulse response of the this was the Fourier transform of the impulse response, and this is now the frequency response function, right? Frequency response function. But this can now be equivalently considered by considering the impedances, and again we describe the impedances. Okay, so if I rewrite the circuit, or rather redraw the circuit in terms of impedances, okay, in terms of impedances, then what is the impedance of this? The impedance of this, again we actually derived the impedances, right? So this is j omega c, right? All right, understandably. So if the input, again the moment I do that, writing impedances in this way essentially takes everything from the time domain to the frequency domain. So now instead of this I have y omega, so output as a function of frequency, I have I omega, current as a function of frequency, and v omega, voltage input as a function of frequency. I consider that to be x, right? Okay, we are going to do that. We are going to solve the exercise of the last class later on, so don't worry. Okay, so with that said, now I can write down the same expression here. So what is the voltage drop across this? Voltage drop across this is just impedance, which is R, into current, plus what is the voltage drop across this? What is the voltage drop across this? So that's given as y omega, right? Rather, something like that. And what is the input? Input is x omega, right? All right. So there is no confusion whatsoever with this, right? Right. But what is y omega? So if I say, if I ask you what is y omega, then what is y omega? Y omega is the voltage drop across this. But what is the voltage drop across this? So let's write down here. What is the voltage drop across this? Current into impedance. Same thing. As electrical engineers, you know that. So what is current? Current is I omega. What is impedance? This. So with that said, yes, exactly. This is why we consider this to be, the reason why we consider this to be h omega, because this is representative of the ratio between the output and the input, right? That is why. In Fourier, after doing the Fourier transform, right? And things will be slightly more clear after writing this, right? So we have I omega, and I can take R plus 1 by j omega c common out of these. I have x omega, all right? So I have I omega into, I have j omega c, j omega rc plus 1 equal to x omega, all right? So I have I omega equal to, this thing can go to the right hand side and becomes a reciprocal. So this is the current through the circuit, but my output was the voltage across the capacitor. This is the current through the circuit. My output was the voltage across the capacitor. So what is the voltage across the capacitor? The voltage across the capacitor is the capacitive impedance into the current through the capacitor, right? What is capacitive impedance? That was j omega c. And again, we actually saw that through Fourier transform. And this is I omega. This is 1 by j omega c, and j omega c, instead of I omega I am writing this j omega c by j omega rc plus 1 by x omega. So what do I have? I have voltage across the capacitor, so this cancels out as 1 by j omega rc plus 1 as x omega, right? All right. So therefore I also, so this actually is completely in agreement with the derivation we did moments ago by applying Fourier transform on the differential equation of the circuit. This is identical to what we derived moments ago, right? Now what if, if the input is an impulse, if the input is an impulse, right? If the input is an impulse, then the output is the impulse response of the circuit. If the input is an impulse, then the output is the impulse response of the circuit, right? Impulse response of the system. Then with that said, what is this? What is the Fourier transform of this? The Fourier transform of this is equal to 1. Then what is the impulse response? What is the impulse response? If the impulse response is, let's find out. What is the output? When the input is, what is the Fourier transform of the output when the input is the unit impulse? Of course, just do that, multiply with 1. So I have 1 by j omega RC plus 1. So this is the Fourier transform of the impulse response. So this is the Fourier transform of the impulse response, right? All right. So how do I write Fourier transform of the impulse response? I write it as h omega. That's the Fourier transform of the impulse response. I write it as h omega. All right. So this is the Fourier transform of the impulse response, and this is the representation. So we use h omega to represent Fourier transform of the impulse response, right? So that is what I said here. So this is the Fourier transform of the impulse response. Why? This is the reason. All right. So we just apply Laplace Fourier transform on everything and take the ratio of the Fourier transform of the output to that of the input. Okay. This is nothing but this y omega by x omega, right? And this is nothing but the Fourier transform of the impulse response. And what is Fourier transform of the impulse response? The Fourier transform of the impulse response is also the frequency response. Now, and we know that the Fourier transform of the impulse response is also called the frequency response. Right? So this is just the frequency response, same thing, right? So h omega is both the impulse response, Fourier transform of the impulse response and the frequency response of the system. This is how the system responds to different frequencies, right? Now I have the same electrical circuit. Now I am interested about exciting the circuit with different sinusoids. Let's see how the circuit behaves. And again, we shall. Again, I'm trying my best to simplify things as far as practicable here. And I ran out of page. All right. All right. So let's take this. Let's consider this. Again, let's consider this. This is the output. All right. Output is the voltage across this, and the input voltage was xt. Now, what if, my question is this, now if xt is, now let me give you some values here. Let me give you some values. Okay, say, let's say this is 1 ohm and say this is 1 farad. Very bad example, but let's deal with this. Okay, this is 1 ohm, this is 1 farad, and All right. We had some issues with the internet, and you people, as you people have might have suggested, the even the internet couldn't take it anymore, right? All right, right. So that's the Arnold Schwarzenegger quote. Right. All right. So I wanted to end with an example. I mean, at least we should do an example, right? Small example, like that. Right. So right. With that said, let's consider. Let's start this with a with few sinusoidal signals, right? Say my input is, consider these, cos 0.2 t. What is the output? I want the output. I want to calculate the output. Okay. Say again, my input is cos 0.5 t. What is the output to this circuit? Say input is cos t. What is the output? Say input is cos 2t. Question is, what is the output? And let's calculate the outputs. Of course, we don't have to calculate anything, right? Because from the frequency response idea, we already know how we calculate the output. Simply try to understand. All of these have magnitudes 1, right? So from this expression, I know that A is equal to 1, right? So the output's magnitude will be entirely determined by the mod of this, right? So for this, what is the value of omega here? What is the value of omega here? Omega is 0.2 radian per second, right? So omega is 0.2 radian per second. So what is the value of omega? 0.2 radian per second, right? So the output is 1 by mod 1 plus j into 0.2. So instead of omega, I have put that. Output would be cos 0.2 t plus angle of this. Okay, let me pull this slightly onto the left. Okay, so this is the angle of this. All right, so question is, what is this calculation? What is the output here? All right, recall this is just the impedance of this, kind of the impedance of the circuit, right? So the answer is 1 by root over 1 plus 0.2 square, right? And I have cos 0.2 t. And what is the angle here? What is the angle of this quantity for this particular scenario? What is the angle of this quantity? Let me again write down here. Okay, so what is the mod here? Of course, that's going to be root over this for this particular example. And what is the angle here? That's going to be angle of 1 minus angle of 1 plus, so this is going to be angle of 1 minus angle of 1 plus j omega. So angle of 1 is a positive real number, so that's 0 minus, and this is tan inverse omega by 1. So this is tan inverse omega. So this is minus tan inverse omega, right? So angle of 1 is a positive real number, so that's 1, so phase angle, and here that's the phase angle, right? So tan inverse omega. So here, so I have minus tan inverse 0.2. Do the calculation. That's the output voltage for that particular scenario. All right. Consider the next situation. Similarly, what is the output here? The output would be 1 by root over 1 plus 0.5 square and then cos 0.5 t minus tan inverse 0.5. That's the output here. Do the calculation. And in the next class, we shall see where from this calculation we can infer very interesting things about the system, and we shall actually talk about those and how we design filters and such based on this knowledge. So this is going to be root over 1 plus 1 square. So this is 1. The frequency is 1 radian per second. So this is going to be cos t minus tan inverse 1. Right? Similarly here, the output is going to be root over 1 plus 2 square cos 2t minus tan inverse 2, right? So as the frequency increases, as you can see, as the frequency increases, what happens? As the frequency of the sinusoid gradually increases, so that is the question, right? No. All of the angles are in radians. None of them are in degrees. Every angle is in radian. Right? This is in radian. Okay. So you do write degree, it is just do simple electrical engineering calculation, but yeah, you cannot just add degrees here, right? You have to do it in radian. So everything is in radian here. So that's in radian. So again, consider xt is equal to cos 10t, and the output becomes, of course, 1 by root over 1 plus 10 square cos 10t minus tan inverse 10. All right. So as you can see, the amplitude is actually gradually decreasing. The amplitude was originally this one, right? And now the amplitude is gradually decreasing, right? So the amplitude of the output, amplitude response, okay, so amplitude response, namely this mod h omega. So here in this particular scenario is root over 1 by 1 plus omega square. So amplitude of the output is gradually decreasing as the frequency increases. So if I do try to plot it, what should it look like? So this is omega, okay? Okay, this is omega. So when this omega is very small, namely a 0, okay? When omega is 0, what is the amplitude of the output? Or rather very close to 0. When omega is very close to 0, if this is very close to 0, what is the amplitude of the output? When omega is very close to 0, what is the amplitude of the output? That's 1, right? That's 1, right? So amplitude of the output is 1 when omega is very close to 0. Okay? Now omega has become, for example, 0.2. What happened to the amplitude? Amplitude has decreased because this number is going to be larger than 1. Then frequency has become 0.5 radian per second. Amplitude has decreased even further. Frequency has become 1 radian per second. Amplitude has decreased even further. Frequency has become 2 radian per second. Amplitude has decreased even further. So amplitude here is gradually decreasing, right? And so on, right? So something like that is happening with the amplitude, and gradually, as you will see, that it will sort of become like this. So as omega becomes very large, gradually the amplitude becomes very close to 0, right? Hardly any amplitude will remain. So when omega is, say, for example, 1000, right? So this becomes like 10 lakh, right? So yes. So if I now join these lines and say this is the increasing value of frequency here, so this is maybe, I don't know, this is maybe 10,000 radian per second and so on, when the amplitude has become very, very, very small. So if I draw these, and again, if I draw this in a slightly more sensible manner, like a person who can actually draw, what do you see? You see that this system or this simple RC circuit lets lower frequencies pass without much attenuation, right? So just like amplification, the term attenuation simply means that the amplitude of the signal has decreased. If the amplitude of a signal gets increased, it's called amplification. Then when the amplitude of a signal decreases, it's called attenuation, right? So for this system lets signals with lower frequencies pass with small attenuation, right? So if the frequency is very small, then attenuation is very small, right? So what I mean that the reduction in amplitude is also small, but as the frequency increases, the reduction in amplitude increases, right? The amplitude is decreased much more and more, right? So what I say is that when amplitude is very small, there is hardly any reduction in when the frequency is very small, frequency of the input signal is very small, then there is hardly any reduction in amplitude, right? But as the frequency increases, right, say this is, for example, say this is 1, okay, as the frequency increases, the amplitude of the output signal also decreases. So when the frequency increases, say for example frequency has become 10, the output of the input signal, its output signal has decreased. When the frequency increases, then the amplitude of the output signal has also decreased. When the frequency increases, the amplitude of the output signal decreases, like that, right? As the frequency increases, the amplitude of the output signal decreases. So now this system kind of does a differential behavior on the signal, kind of. So signals that have lower frequencies, it lets those signals pass without much of any attenuation. But signals that have high frequencies in it, it lets these signals pass with a large attenuation. So in other sense, if the signals that is coming in has a very high frequency, the system will not let it pass, right? The amplitude will become so small as if in the output that signal will have no result, right? So if I give it as input of 1000 hertz, 1000 radian per second frequency, the output will become so small in amplitude that it will be hardly visible in the output, right? Right? So in a sense, this system passes low frequency signals and blocks high frequency signal. So in a sense, I can say, in a sense, this system passes low frequency signals. So passes means lets them go with small reduction in amplitude, and blocks, and by blocks I mean it lets the signal go with a huge reduction in amplitude. Blocks high frequency signals. So this in a sense is a system that passes low frequency signals, and by passes I mean let low frequency signals go without any large modification in the amplitude. But if you send in a high frequency signal, it blocks it, and by blocks I mean it lets the signal pass but with a great reduction in amplitude. This is called a low pass filter. Thus it is known as a low pass filter. Filter that lets lower frequencies go and blocks higher frequencies. Of course, the high pass filter thing would be just the other way around, but this is a low pass filter. Okay, so this simple RC circuit, when you excite the input like this and pass it up, and when you pass in different signals here, okay, so the lower frequencies will be attenuated less, the higher frequencies will be attenuated more, right? So that is why this thing is known as a low pass filter. So I think this idea is clear now, right? So again, we shall extend this idea later on and in our next class, and do try to figure out how different filters really work, how different systems, or rather different circuits, we people are electrical engineers after all, how different circuit behaves differently in the frequency domain, right? And you might have already felt this, that in the same plot I am writing 1, 10, 100,000, right? This is not moving linearly here, right? This is a logarithmic scale. We shall discuss that later on. This is not a linear scale, it's a logarithmic scale. Okay. So I have a same gap for 1, same gap for 10, same gap for 100, same gap for 1000, something like that. It's called a logarithmic scale, and we shall discuss that. Okay. But in any case, feel free to ask any question that you might have. We took very long, okay, to discuss everything, but I wanted to end at a point where the discussion is more or less complete, right? So we have really talked about the frequency response of systems, and talking about the RL circuit, we shall do that on the next class if you are still somehow unable to. And I mean, few of you, like 3 or 4 of you, are actually able to solve the RL circuit. Okay, get hold of them, or yes, if I take a logarithmic scale, it cramps the scale, and we shall see how these things really work in a later class. Okay, we shall deal with this properly. In any case, if you have any query, feel free to ask at this point. Otherwise, we shall end our discussion, and we shall actually continue our discussion in the next class. Okay. We shall see how high pass filters work, how band pass filters work, how band stop filters really work, and different circuits have different configurations, and from which how we can easily draw these kind of frequency response functions and everything. We shall actually learn that. This is the again amplitude of H. In any case, if you have any query, feel free to ask any question. I'll be here for 2 more minutes. Otherwise, we shall end our discussion today. And well, just as a homework, small homework. Again, this has got nothing to do with the frequency response. I mean, but you don't have to draw this in any case. Okay, same this. My problem would be, I have a simple question for you. Okay, simple question for you. Say I have a system. So homework, right? I have a system whose impulse response this is the impulse response. This is A rect t by 2t. That's the impulse response of the system. Okay, and the system is excited with an input like our previous example. Okay, let's consider this, remove this A. Okay, with cos 5t. So of course there is no ut, so this input has been there for a very long time. Okay, find the output. Through the concept of frequency response. Okay, based on our discussion today, try to figure out the output of the system. In any case, that will be the end of our discussion today, and thank you very much for being patiently here for 2 hours 20 minutes. That's a very long time. Not even many movies of 2 hours 20 minutes. In any case, thank you very much. I'll be ending our discussion today here. Again, feel free to drop me an email if you have any query, and this video will be there. Those who have missed some parts of it, you can go back and watch them. And if you have any query, feel free to drop me an email. I shall definitely be answering your queries. And try submitting this and try solving this at least. Put your hands on, right? You might end up with a wrong answer, but that's not the point. The point is that you tried solving this. That's the important thing. All right. In any case, that will be the end of our discussion today. Thank you very much for being here. I shall see you on Friday.